Well, good afternoon, ladies and gentlemen. Again, sorry I can't be there with you today on Monday, but we're going to do a little bit of Chapter 14 together with just a real short lesson today. Of course, as of right now, you have viewed the Mount Everest video, and I hope you like that. You also handed in your Mount Everest video sheet to Ms. Couch. Second thing, you've worked on Chapter 14 yourself, so these questions probably won't come as a surprise to you today. But we're going to look at questions 1 through 14 for a few minutes today in class and talk about behavior of gases and the factors that affect them. So our first thing that we're looking at today is actually the 3 factors that affect gas behavior. And of course you can even see them here on the main screen as well for that one. The 3 things are called pressure, volume, and temperature. So pressure, volume, and temperature. And of course we like to call them P, V, and T. P, V, and T. Those are the 3 letters that you're going to be using most often in this unit. Last Thursday we talked about gas pressure specifically and how it's created by collisions between gas particles. We're also going to talk about the volume that you contain those gases in and the temperature of the gas and how that makes a difference. Furthermore, last Thursday, again, several of you told me in advance of today's lesson that you knew what would happen if you actually took a container and made it smaller and you had gas trapped in that container. You said that the gas would actually develop a higher pressure if it was put in a smaller container. Well, then question 2 is probably no surprise to you then. If the volume of the container were to triple, if it were to get bigger, what would happen to the pressure then? And so for number 2, hopefully you found that the pressure would actually decrease by a factor of 3. So if volume goes up by a factor of 3, pressure will go down by a factor of 3. You could also say pressure would be multiplied by 1/3. Okay, pressure would be multiplied by 1/3, and that would still be true for this one. Now, with number 2, there was a scientist who first noticed this relationship between pressure and volume. And it was the first gas law developed in the 1880s. The scientist's name was Robert Boyle. And so we call our first gas law or law of behavior of gases Boyle's law. Okay, Boyle's law. And so for number 3 things that I want you to underline here for this one. The first thing is Boyle's law is always constant temperature. So those are 2 of the 3 words I'd like you to underline. He actually never changed temperature in his experimentation. Temperature was constant. And of course, when he did leave temperature constant, he found that pressure varies inversely with volume. So circle the word inversely. Okay, inversely. This is the only inverse relationship we have today. And so when you actually go and look at the graph here, it's going to be an inverse relationship between pressure and volume here in just a second. But number 4 is what you're using on your classwork today. Notice it's a real simple formula. It's plugging in and solving, so not very difficult algebra today. But number 4 is P1 times V1 equals P2 times V2. And again, those variables here represent the initial conditions. P1 and V1 are the initial conditions of the gas. P2 and V2 are the final conditions of the gas. So that's what the 1s and 2s will mean throughout all of this. And so I put my pressure on here for number 5, and I'm going to measure it in atmospheres. Volume I'll measure in liters. And you notice the graph that you got in the text there for number 5. It's a curved line, okay, a curved line. It shows that as pressure goes down, volume goes up for this one. And again, it's always a curved or parabolic line when you have an inverse relationship. No matter what the gas law or expression is, again, it's always curved. But Boyle's law will be the only inverse relationship we have. Now, at this point, notice number 6 is going to ask you to use your calculator. So if you have your own calculator, I'm going to have you take it out. If you need to go to station 11 and 12 and get a calculator from the boxes, feel free to do so. For those of you that want to go ahead and read number 6, feel free to take a few moments and read through number 6 here today. And you'll notice that problem 6, you see that I underlined it on the smart board here. It says temperature is constant. And that's how I know that I actually want to use Boyle's Law. Again, we will keep temperature constant when we do Boyle's Law problems. I had worked Boyle's Law earlier here in the unit, and so I'm going to erase this for that one and get that off the screen. I had to come back and re-video a little bit here on this one. Ran out of memory on my card, so I'm going to erase a little bit of this. But you notice there's my Boyle's Law formula, and this is problem 6. I just brought it over to the smart board so that it would be easier to work with. And so I have my P1 times V1 equals P2 times V2 set up. And in the first line of the problem, you'll notice what I've got. I've got volume 1. It's 17 milliliters. Remember, milliliters, liters, gallons, pints, those are always going to be volume units. They measure the amount of space an object takes up. Pressure is in the second part of sentence 1. It is 1.1 atmospheres. Okay? I go on to sentence 2, and it tells me that my new pressure is 720 torr. And that I'm looking for volume 2. Okay? So I'm ready to go ahead and solve, right? Several of you probably caught early on that there is a problem here with this number 6. The pressure units don't match. And we need them to match. Okay? We need them to match. Otherwise, they won't cancel out to give us volume. So consider if you happen to take 720 torr and you wanted to convert it to atmospheres. Well, think about what we learned last Thursday. Look to your left over here on the side and actually see the relationship. If I want to go from torr to atmospheres, 1 atmosphere, class, how many torr does it equal? And if you look to your left, you see that it equals 760. And so we're going to divide 720 by 760. Always take your given divided by the 760. And so 720 divided by 760, do it in your calculator. That gives you 0.95 atmospheres. And now you can plug that in for 720 torr, and you have pressure units that match. And that's a good thing. Now, of course, if I were there with you today, I would ask you, how do you solve this problem? Okay, of course, you would tell me, we're going to divide by 0.95 atmospheres, which is exactly right. And when you divide by the atmospheres, again, these atmospheres will cancel, and it just leaves you with volume 2 in milliliters. Okay? So do 1.1 times 17 divided by 0.95. And it'll give you about 19.7 milliliters for volume 2. So we're done, right? Well, some of you may have caught what we have up here in the circle for this one. They do want the final volume in liters. So sometimes they test you on your metric system as well. So if you look to your left again, if you want to go from milliliters to the base, to the liter step, you notice you're going to move 3 places to the left because you're going up the staircase. So 3 places to the left gives me 0.0197 liters. And that's your final answer for number 6. 0.0197. Okay? So it's not too bad, and the ones on the classwork, most of them have pressures that match. There will be 2 of them in which the pressures don't match, and you'll have to use the expression to your left, okay, to make the pressures match. But hopefully that wasn't too bad, just some basic algebra to solve. Now, this actually shows the relationship between pressure and volume. But that's not the only relationship we have for gases. Along comes number 7, and there's a new scientist in the 1890s who actually experiments with gases, but he holds pressure constant. His name is Jacques Charles. He's a French scientist. And he observed something that maybe you have observed before. If you were to take a balloon and place it in the freezer for number 7, it would shrink. Okay, it would shrink. The gas particles move closer together because of the cold temperature, and so the volume or the space they occupy lowers. Same thing if you've ever had balloons in a hot car on a summer's day before. Again, you probably didn't have balloons for long. Reason being is that the gas expands when it's hot, and it could expand so much that it makes the balloon pop. So you may have witnessed one or the other of those, and Jacques Charles witnessed that. And so he decided to hold pressure constant. So underline that for me in your definition number 8. This is how you know it's Charles' law, constant pressure. Okay? But Charles found that temperature varies directly with volume, that it's a direct relationship. So that's different from Boyle's law. We have the direct relationship now in number 9, and this is what a graph of Charles' law looks like. Volume on the y, temperature on the x. You get a straight diagonal line. Notice, it can't be straight horizontal. That means that volume's not changing. It can't be straight vertical. That would mean temperature's not changing. But in Charles' law, temperature and volume do change. So it has to be straight diagonal. Last thing you'll notice is that the temperature is measured in Kelvin. Well, why would they measure the temperature in Kelvin? Okay, why would you measure temperature in Kelvin? So I'm going to go back to my previous slide. And in number 10, you probably found your formula for Charles' law to also be pretty simple. It's V1 over T1 equals V2 over T2. Again, 1s are the initial conditions, 2s are the final conditions. But realize if you use negative Celsius temperatures or negative Fahrenheit temperatures, you run the risk of getting negative volume. Negative volume doesn't exist. And so we have to use a temperature scale that ends at 0. And the Kelvin scale does not have any negative numbers on it. And so Kelvin's a great scale to use here in order to get positive volumes and positive pressures at all times. Now, if you need a little reminder, again, you can write this in number 10. Remember that if you want to convert Celsius to Kelvin, the magic number you add is 273. Okay, 273 is your magic number here. Okay? So that's a little reminder. And again, several of you told me that even back in chapter 10. All right. So question 11. Take a few moments here with question 11 and read through it. We're almost there. But take a few moments to read through it and get your calculator ready for that one. Notice the yellow part. The temperature has to be in Kelvin for Charles' law. So this is number 11. Okay. And again, I'm going to go to the Smart Notebook, and you'll see number 11 here for this one. The other reason I know that this is Charles' law is because, notice the end. It says pressure is constant, or assume constant pressure. So, you see the first sentence here. It says a 12-liter container of gas has its volume and its temperature raised to 15 liters and 65 degrees Celsius. So notice this is an interesting problem. You do have to read these problems carefully. Volume 1 is 12 liters. Volume 2, after the volume has been raised, is 15 liters. So we see our change in volume. Volume went up. Okay? Then you notice that we have a new temperature of 65 degrees Celsius. It wants to know what is the original temperature of the gas in Kelvin. Okay? So 65 degrees Celsius is our Celsius temp. We need to change it to Kelvin though. So again, if you add this to 273, you end up with 338 Kelvin. Okay? And we're looking for T1. Now, of course, most of you realize that in order to solve this problem, it's going to come down to cross multiply. Okay? We need to cross multiply here. And you always go in the direction that is complete, that has no missing variables. So we're going to go left to right first, as you know from probably middle school or elementary school. So 12 liters times 338 Kelvin divided by 15 liters. And notice how this will allow the liters to cancel. So cross multiply. 12 times 338 divided by whatever is in the right to left direction, which is 15 this time. Okay? So take your calculator and take a few moments here to actually solve this problem and get your new temperature, your original temperature there. Excuse me. Okay, and I get T1 as 270.4 Kelvin. 270.4 Kelvin. Okay. And that's your final answer for number 11. And those are pretty straightforward. The only tricky thing is remember to convert those temperatures to Kelvin. You do have to go to Kelvin first. Had they asked you to convert the final answer to Celsius, you would do that at the end. You would subtract 273 at the end of the problem. Okay, so that's number 11. And hopefully you didn't think that was too bad. And so now we'll finish up with our last little thing. So, pardon me again, this gentleman sometimes doesn't even get credit in textbooks for actually coming up with the third gas law. This gas law, again, is sort of the leftovers. As you notice, once you figured out what happens at constant temperature and constant pressure, the only thing left is to hold volume constant. Okay, so for number 12, I'm going to have you underline constant volume. This is a gentleman named Gay-Lussac, Albert Gay-Lussac. Again, he actually did constant volume, and he found that pressure varies directly with temperature. And so, of course, his gas law, I'm going to change my V to a P down here at the bottom. It also has a straight diagonal line. You didn't have to answer that question again, but it would have a straight diagonal line. And notice Gay-Lussac's law is going to be P1 over T1 equals P2 over T2. Very similar to Charles' law. Temperatures would have to be in Kelvin again for number 13. Okay? Now, we're going to do one last problem, and that's number 14 today. And number 14 gives you an example of the Gay-Lussac's law. Again, notice here at the end, this is why 14 is Gay-Lussac's law. Assume constant volume. So take a few minutes, and take a few seconds, I should say, and read through that problem. Okay. So final example of Gay-Lussac's law is up here. And it says I have a gas stored at a pressure of 760 millimeters of mercury, and it's also at 25 degrees Celsius, which just happens to be room temperature. It says what happens to the gas pressure when the temperature rises to 50 degrees Celsius, and what's the new pressure? Well, class, to answer this first part, what happens to the gas pressure when the temperature rises? Remember that this is a direct relationship. So if pressure ends up going, if temperature ends up going up, then pressure will end up going and rising as well. So it will also go up. So we have an idea of what's happening, and that helps sometimes on multiple choice questions if you know the pressure is going to have to be higher than 760. You can eliminate some answer choices. So plugging in here, we have 760 millimeters of mercury. Okay. 25 degrees Celsius, remember to convert that temperature to Kelvin. So if you add 273 to that, it becomes 298 Kelvin. Okay? I don't know P2, so that's my missing piece, but I do know that my new temperature is 50 degrees Celsius. So if I add that to 273, that gives me 323 Kelvin. Okay? And so, again, pretty easy with the cross multiplying. We can go left to right again. And we'll do 760 times 323 divided by 298. Okay? And like I said, we should see that our pressure would rise. So hopefully it's no surprise to you that pressure 2 ends up being higher. It's 823.7 millimeters of mercury. Okay, so pretty simple algebra, right? All right. Well, hopefully you find it to be simple. I'm going to ask you to actually work at your desk instead of going to the lab stations. I want you to stay where you will concentrate. You are welcome to ask neighbors, okay? Ask neighbors, again, for help and assistance. But Miss Couch is now going to give you a sheet that actually has Boyle's Law on the front left, Charles' Law on the front right. Remember to change those temperatures to Kelvin. That's important. You may want to go ahead and do that first on the front right. And then on the front back, there is a left side called Gay-Lussac's Law. I just want you to do those 3 sections. Do not do the combined gas law tonight. So don't do the combined gas law this evening. Leave the right side, back right, off. Okay? So try these this evening. Real simple. But do remember to change those temperatures to Kelvin for Charles' Law and for Gay-Lussac's Law. All right? Thank you for your attention on this today. And again, I hope you have a good afternoon.